will continue with the axial, the effect of axial load on this pile because of the pile group effect. So, the procedure to calculate, if you have a multi-layered soil, what we need to really worry is calculation of average properties for the modulus value. That is where the whole issue. In fact, we were talking about when we are doing the TJet for various soil. If you are developing a TJet at a particular location, what happens to the previous layers is the most important one. So, if you look at most of the procedure developed earlier, they always will be talk about a single layer methodology. In fact, even the API equations what we have just discussed, that actually does not in fact discuss about how you treat with the multi-layered soil. So, we have to be cautious. So, in this principle also the modulus value is playing a major role, because you can see the effect of settlement. So, an approximate procedure needs to be developed for computing the C soil. What we normally do in the practice is to carry out a separate analysis at various load levels and find out what is the displacement of the pile, and then calculate calculate the value of the soil modulus for the multi-layered soil. But in classroom exercise it will be very difficult, because without a computer you can't do it. So, what we normally can adapt in our exercise, you can take an average value of in a multi-layered soil and use it for the computational purposes. And Poisson's ratio, length of the pile, and value of rho, which is nothing but the ratio of the modulus at half distance to the full length. That means somewhere here to the toe of the pile, which is going to be one of the parameter. And the relative stiffness, which we were, I think if you remember when we were deriving lateral pile capacity various methods. So, Kr is actually a stiffness factor, Ei is the pile stiffness, whereas the E soil is taken here with L power 4, is very similar to your cantilever problem. So, Kr will be a representative parameter representing the pile and the soil stiffness, and this rho will tell how the soil modulus varies along the length of the pile, and typically taken as the ratio of the value of soil modulus at half depth to the pile toe. And the procedure to calculate, because we were looking at jet value something like this. The increased deflection is the deflection of single pile for the particular load multiplied by the jet m, which is basically a deflection multiplier or jet multiplier, and which is taken as 1 plus alpha v. So, we are interested in finding out what is this alpha v. Procedure described here is basically displacement of pile due to load on adjacent pile divided by displacement of pile due to load on the pile itself. So, it is like just like a unit load problem. You apply a load on the pile, find out what is the displacement, that is the displacement due to that load on that pile, and then displacement of the same pile due to load on the neighboring pile, and just this is only we are talking about 2 piles. Suppose if you have several piles, so you have to cumulatively add the effects all around. So, we can do a loop computational program, just take effect one by one, and basically the alpha v is derived as this, is a semi-empirical formula derived by Joseph Bowles, and basically the parameter zeta and psi, this is length to diameter, this is spacing to diameter, and various parameters involved here is just given a notation. If you substitute here, it will become too big. So, that is why I have taken little subdivisional parameters. But what is the involvement is the spacing, diameter, length, and then the variation of modulus, Poisson's ratio. These are the parameters involved in order to compute this alpha factor, which will be added to 1 plus alpha v. So, basically as long as you have higher number, you will get the effect. So, that much of increased deflection will happen depending on the spacing, to diameter ratio, length to diameter ratio, and then the Poisson's ratio, increase in the soil modulus value below half depth. So, basically if you look at these parameters, what else is unknown? For a given the same value, whatever you see here, instead of computing here, he has developed actually several charts for the given values of Kr, length to diameter ratio, based on the equations what we have seen, and you could possibly read it from the charts that I have just copied from the book. So, you can straight away use it whenever you have only 2 pile system, because typically you can't use this procedure whatever I have given here, it is only specifically for 2 pile system, and basic if you have more than 2 piles you have to come up with some additional methodology to take the effect into it. Various charts, I think there are so many charts, I think some 10 charts are there, just to give you a guidance, so that in case if you want to use it for practice you can use this. So, alpha v is in the vertical axis and S by D ratio, and this half the graph on the right hand side is just D by S ratio instead of S by D ratio. So, you can up to this you can use either D by E ratio or S by D ratio, the alpha by v value can be read for a different values of Kr. So, you have Kr values from 10 to 1000 and L by D ratio of 10 and 0.5. So, the next graph will show you for different L by D ratio, different Poisson's ratio. So, just repetitive of them, I think some 10 charts are available. So, basically alpha v can be computed. So, ultimately once you have the alpha v value, then you calculate your increased reflection, you just start plotting your graph. So, if you look at several graphs 0.5, you see here is 0.5, 10, this is 25 and then 50. So, if you look for different Poisson's ratio, you have to look at the original publication. I have only taken some few samples, 100, and then effect of ES on pile settlement, basically for a L by D ratio of 50.5 and H by L is very large. So, this is the last graph you can find from that book. So, typically how the T jet, the effect of T jet on the pile group effect, you can see here the original is in blue color, basically the T jet graph drawn for, I think this is typically for a clay type of soil. So, you can see here several coordinates were given in API. So, you can draw that, and then after multiplying, this is basically T multiplier, not jet multiplier. So, for a given given displacement, the modified the T jet curve has got lower capacity than the original capacity is say 1. So, reduced capacity is about 50%. So, this is basically a multiplier on the capacity. Suppose if you do a, this is also T multiplier, if you do a Y multiplier, jet multiplier, it will not look like this, because the deflection will be more for the same. So, this point will be, you have the deflection of 10 or maybe 8 mm for full capacity. So, what will happen is if you multiply Y multiplier, the deflection will be more, but the capacity is same. So, either way you can deal with it. Most of the time in practice we use a T multiplier. Similarly, for T jet curve, for T multiplier is basically, you see here the original graph is the blue one, whereas the reduced capacity for the same deflection is this much. So, we are just having the same capacity, scale the deflection to a same level, and only the capacity is reduced. If you want to use jet multiplier, this is what will happen. Just I was trying to explain. For the capacity of the same capacity, see the red color one is the original and the green color one is the after multiplying with. So, always jet multiplier is going to be greater than 1. So, you will see that the more deflection will happen. So, the shape of the graph is same, except that it is getting shifted by that much amount, whatever be the, if it is a jet multiplier of 2, 1 mm become 2 mm or 10 mm become 20 mm for the full capacity to achieve. So, what it means is you will take more deflection, basically that is the idea. For sand, I think this is for clay and this is for sand, just to give you an idea how and what happens when you apply the multiplication factors. The next one is basically the effect of these group or the spacing of piles on lateral capacity. Similar to the axial capacity, we will also have a Y multiplier instead of jet multiplier, because that was vertical and this was going to be lateral. So, Y multiplied by Ym, and again instead of alpha vertical you calculate the alpha horizontal. So, it is a similar procedure, and basically one of the problem is the modulus value what we were taking average, here may be very difficult to do average, because the effect of the pile displacement on the soil is varying along the length, because you can see less effect on the pile below and more effect on the soil near the the seabed and just little bit down. So, in that case we have to find a methodology to find out the values of modulus along the depth of the pile. So, typically if you look at this picture, three piles arranged in a corner of a jacket leg, and basically you have a overlap here, and this is the one that we were thinking of taking into account. So, you see here, if the loading is like this, so some amount of shadowing effect on this pile because of this pile, and of course there will be a very little depending on what is the load. Suppose if the load is in this direction, there will be full shadowing. So, now horizontal load, it is going to be dependent on direction of loading, and what we need to do is, generally in practice we take the most the onerous case in which the group effect is going to be higher. So, as I mentioned for vertical pile, so you can see here is a cumulative effect of a particular pile displacement because of the loads on the neighboring piles. So, you could add from 1 to n number of piles. It is a generalized procedure given in a textbook, which generally we use it in practice, basically Joseph Bowles' book. It is based on a simple matrix methodology. In fact, you might have studied in your structural analysis program matrix method of solution by dividing the sections the pile into several subsegments and solve for the displacement along the length and all along the full length. Once you find, then you just iterate for all other groups. So, basically y is the multiplication factor, alpha is the multiplication factor for the displacement of the jth pile due to ith load. So, that is the notation, and just keep doing for all the piles, and beta is the angle between the two piles which is going to form the group, and the load on this pile is Pi and load on this pile is Pj. So, just you will have a k number of piles in the group. The spacing is S. Typically again a similar idea. Once you find out y multiplier, you can just increase something like this. This is the original, this is the increased deflection for the same, because this much increase is due to the load from the neighboring pile. It is not because of the load on that pile itself. So, in order to find out a combined soil modulus, normally what we do is we construct this type of diagram. So, you have to do a computer analysis, apply various loading and try to derive the displacement of the pile head or pile at any location and derive the relationship between load versus displacement. So, this slope of the graph will give you an idea about what is the kind of modulus, the combined modulus of the total soil. So, this cannot be found by simple means of hand calculations. That is one of the the problem associated with this methodology. Somehow you have to find out an average behavior of the total soil layers when you have more than one layer. So, that is something you have to find out to establish because this is very similar to a load displacement characteristics in your pile load test. Suppose if you are able to establish this graph in the pile load test, that will give you a good average behavior of the total soil layers. If you are not having pile load test, then you have to do something similar like a numerical method to solve the representative E parameters, and you can use that value for your hand calculations. Similarly, when you are applying a horizontal load, you could also need to find out apply the load and increment it several steps and then plot with respect to horizontal. This will give you a horizontal soil modulus for use in your modification work, and mostly it is easy, something similar what we were looking at pile soil interaction softwares. You can apply load in various steps, apply the obtain the displacements and plot this type of relationship to get the E value. So, the simple procedure to use the chart given by Bowles' book is the procedure given here. Initial value of soil modulus can be obtained from vertical load deflection curve, which I think we just have, and calculate the Kr value, which is the relative soil to pile stiffness. Obtain I value, the interaction factor from the chart using the Kr value and the L by D. We are going to see the chart little bit later, and E value can also be back calculated after obtaining delta H, and the I value you have read from the chart, and recalculate the Kr value, which is because E soil is going to affect your Kr value. So, as long as your E soil value is correct, then your Kr, because you are going to read I value from the chart. So, as long as Kr is incorrect, you are going to have a wrong value of reading. So, you just do a recalculate few times, then read the chart for alpha h, this is not ah, alpha h, for different values of Kr and beta. Beta is the angle of loading. So, just a few procedures to just. So, if you look at the whole idea, the representative soil parameter is going to be very important parameter in deciding what will be the alpha value. So, there is a chart for I, which is an influence factor depending on the soil to pile stiffness, which is given for various. So, this d is the diameter, because the other one was capital D. So, I did not modify just because it is given in the textbook, and given Poisson's ratio is 0.5. Various values of L by D is given here, and influence factors for different values of Kr. So, alpha h is the additional displacement caused by adjacent pile divided by displacement of pile caused by its own loading. So, neighboring pile. So, it could be as big as the original displacement if the load is so much, or if it is smaller load, you will have a fraction of displacement increase on the. So, normally you will not have a very big alpha h value, but when you add with 1, you may have 1.2, 1.3, 1.5, and as the effect increases and the spacing is closer, you will see that alpha h value can reach as much as 2. Some cases you will find that you will have to use a deflection increase of 2 times of the original deflection. And then the various charts for reading the alpha h value is given here for similar idea, beta 0 degree, 90 degree, and mu is 0.5. Here what is the difference? So, here is S by D alpha h for Kr value of 0.1, Kr value of 10 to the power minus 5. So, you have 2 different Kr values, and this is typically for 2 pile system. So, basically that is. So, when you go back to this picture, based on this numerical scheme, he has developed this and solved the equation in computer and plotted these graphs for 2 piles. So, suppose if you are interested in solving for more than 2 piles, you have to go back to the matrix equation and then solve for your particular. So, some of the programs commercially available can do this exercise. Instead of you go and use these charts, you can actually buy the program and use for your 2 pile system, 3 pile system, but for most of the practical applications, I think 2 pile system is okay. Instead of buying a software, you can use these charts and then slightly approximate, because you are reading these charts, because you can see here the values can jump very big to small unless you are careful in calculating the Kr value correct and reading the chart carefully, because then it may influence reasonably higher. So, this is for two different values of Kr, and for the solid line is for 0 degree and the dotted line is for 90 degree. So, that means perpendicular loading, and mu value is 0.5. 0.5 only difference is 10 power minus 3 from minus 0.5 minus 3, here it is 10, and then seems to be same or different, seems to be same. Oh, this is free headed pile, this is fixture headed pile. So, there will be another repetition of 3 more graphs. Mostly you will need to read the fixture headed pile, because for offshore steel type jackets where the pile head is connected to the jacket leg, you will not be able to treat it as a free headed pile unless you have a onshore or maybe near shore structure where the pile head is free to move, whereas most of the cases you will be having fixture headed pile for our jacket type of structures. This is for rotation anyway, which is not going to be very much useful. A typical example is given here, basically Randolph and Worth for axial and the lateral capacity. Similar, whatever we have explained, I have given an example. So, basically the modulus of the pile is this much, diameter and the thickness, length of the pile is 85 meter, spacing is 4.38 meters. So, basically you can look at it 2 times of almost 4.38 meters is coming nearly 2 diameter spacing, Poisson's ratio and modulus ratio of the soil linearly increasing from half to full depth, and you have the properties calculated here. and various factors involved in the calculation of alpha v. So, you see here the alpha v comes out to be 1.46, about 1.5. So, there is a 50% increase in the axial deflection, because we have that spacing is just only 2 diameter. So, if you go to 3 diameter, you may find that this may come down to 1.1. Normally we adopt in practice minimum 3 diameter. I think I have already mentioned in initial classes, we should maintain at least minimum 3 diameter at any cost, because most of the codes, whether it is local codes or other codes, they ask for minimum 3 diameter, because the axial capacity reduction, you do not want to see that it is substantially bigger, like this 46% is very big, but 5 to 10% is reasonably acceptable. So, that is why this I just wanted to demonstrate that you can actually go back and calculate for 3 diameter, you will find maybe 10%. If it is 4 diameter, probably you will not find any effect at all on the deflection, it will diminish. Whereas, if you look at the lateral deformation, this will be even bigger effect depending on the type of soil. So, you see here the initial value of soil modulus for a multi-layered soil is given to you in case of examination or in case of your practice. This value is given basically based on computer analysis, because it is a multi-layered soil. So, analysis has been separately done, and then you have got the initial value obtained from the load displacement graph. Otherwise, you have to establish this. So, to establish this, you apply unit load and just keep increasing the load versus displacement and try to get this the slope of the graph will give you the modulus value, and total load applied on the pile itself is so much maximum load, and maximum displacement is this much. So, this gives you a total ultimate behavior, and initial value of Kr can be calculated because you already have been given this number. So, you calculate the Kr, influence factor read from the chart which we were seeing, and revised value of soil based on the new value of IP, and then revised value of Kr, and then again you can go and do a few iterations. If you write a computer program, you can do iterations to make sure that the starting value and the next value, the delta is smaller, so that your error in accuracy is smaller, and then the departure angle of your loading is given to you 45 degrees, because you can go and read it, and then for a value of beta, L by D and Kr, you read the value of alpha h 0.48. So, 1 plus, so you can surprisingly see that this also comes to be 1.46, does not mean that it will be 1.46 for your problem. It so happened that depending on the values of the soil parameters, this can change. So, I think that gives you an idea of a typical pile group effect. What we have looked at is only the deflection and capacities.